So thanks everyone. This is the Lunar Geophysical Network mission. I am the figurehead PI and Renee Weber is the deputy PI. And we couldn't have done this study without one heck of a team that has been put together with a lot of expertise in the physical methods that we're talking about here. And also a big shout out to the Goddard team. You can see down below in the bottom of this particular slide who have done yeoman's work, not only putting together this mission but several others. And you heard earlier in this particular session, and they've done a fantastic job, because we were fortunate to be able to have our study before COVID-19 really hit. So we had an in-person study, but then everything went to hell in a handbasket, and we started working from home. So there's a great shout out to the team here, and especially the folks from Goddard, and especially my deputy PI Renee, who has kept me sane throughout all of this. And so what is the Lunar Geophysical Network mission goal? We have basically one, and that's to understand the initial stages of terrestrial planet. Keep it simple. This is the goal of the mission. And so why are we going to the moon to look at this? Because we believe that the moon not only informs us, of course, about lunar science, but it informs us about solar system science. So we're looking at terrestrial planet evolution. And the moon's history, and some of the tests through this mission is when the moon formed through a giant impact coalescence of material formed a magma ocean. And we had the cumulates that formed the crust, those that floated, and of course those that sank formed the Mare basalt source region. And we believe that the moon is the end member of this terrestrial, because the primary evolution is recorded here, is frozen in time. That's because the small size of the moon, and therefore its heat engine, means differentiation essentially stopped after lunar magma ocean crystallization. And Mare basalt compositions that we've analyzed so far tend to support the consistent with an origin from a source derived from cumulates from that magma ocean. And that this cumulate pile underwent a cumulate overturn, and we are seeing that recorded by the compositions of those basalts. And as we're getting more lunar meteorites, we're seeing that holding true. In terms of geophysics, there was the Apollo had the ALSEP, and there were a lot of geophysical experiments and instruments placed on the moon and data generated. But there's still inconsistencies in some of the data sets. And we can see now that we have a fantastic mission, turned fantastic data, but they are calibrated on the basis of near-side Apollo seismic data. And if we look at the networks set up by Apollo, you can see that they're very focused on the central near side. A number of different geophysical networks is there, and return data for, in some cases, for a number of years. But the issues we have in the two heat flow experiments at Apollo 15 and 17, these were close to a terrain boundary, the terrain between the feldspathic highlands and the prosolar and creep terrains. While magnetometers were deployed at 3 sites, they weren't netly. One was actually used to undertake electromagnetic sounding of the mantle to try and understand compositions. This led to relatively low resolution data that was equivocal in nature, and it also reported only on the prosolar and creep terrain. Massive size monitor network formed a similar triangular small network, a small aperture network on the near side. So the deep structure of the moon has not been resolved in terms of the seismicity or seismic structure. And retroreflectors were placed 3 in the 2 from the Soviet Lunar Cod rovers. They continue to generate data. But we need to expand this network in order to add fidelity to the current data that is being recorded, in order to investigate, for example, things such as the inner core of the moon, which is still ambiguous, and trying to get clarity between these different data sets is something that requires a lunar geophysical network. So we have a lot of science questions we want to look at. That starts off with the overall composition and structure of the moon to tell us about the creation of terrestrial planets. trying to look at and document what the current state or structure and composition of that mantle is, and is it consistent with this magma ocean hypothesis. So we will be testing the lunar magma ocean hypothesis. What is the present heat budget? There's relatively recent magmatism. We've heard from about P60, which is by crater counts thought to be about 1 billion years old, and then the IMPs, which could be less than 100 million or could be more than 3 billion. But that is can the heat engine of the moon produce such recent magmatism? Again, looking at the terrain idea that we now know from Clementine and Prospector, we now know that there are different crustal terrains. What is that? Is that extended into the mantle? And then how did the lunar core? We really haven't thought much about that in terms of core formation hypotheses. And could that core have actually supported a global magnetic field, as is now being suggested by continued sample analysis? And then what is the bulk composition of the moon, and how can that be related to the moon forming impact? So a number of questions that we want to address. We will do that by deploying identical landers, each containing seismometers, heat flow probes, magnetotelluric sounding instruments, and laser retroreflectors. And these would be deployed around the moon to examine structure, composition, not only of the core. And this will be able to address a number of questions that have actually occurred since the Apollo data. For example, what is the origin of these shallow moonquakes, these high teleseismic events? Very unique in terms of other seismic events on the moon. Do they represent movements along thrust faults that we now know to exist? The other thing is, do they present a threat to future human infrastructure that is being considered for the South Pole region of the moon? Do deep moonquakes occur on the far side, the near side? We detected very few deep moonquakes from the far side, and this was considered to be, well, maybe we're just not reading them, or are they just not occurring on the far side? And then what is the true mechanism for triggering these deep moonquakes? The interesting thing about the Apollo seismic data is we have seen the detection of a mantle discontinuity, initially considered to be the base of the lunar magma ocean, but reprocessing tends to make that go away. So we don't know if that's a global layer or an artifact. And again, this needs to be looked at. And then in terms of heat flow layer at the base of the mantle, as suggested by some studies. Looking at the different terrains, how do these unique heat flow budgets relate to the bulk composition of the moon? And then the vertical and lateral variations in structure and composition. We need to calculate bulk composition and understand the structure and overall evolution of the moon in terms of how it relates to the initial stages of terrestrial planet differentiation. So we have this divided into objectives and investigations. Under our one objectives there, we've got 4 of them: define the interior structure, constrain the interior bulk composition, delineate vertical and lateral heterogeneities with the interior of the moon as they relate to the crustal terrains, and then evaluate current seismotectonic activity of the moon. Again, an emerging field of results from LRO. So our investigations then, we have 5 of those, and it's all about determining size, state, and composition of the lunar core, and then this physical stratification within the lunar mantle, and look at the thick and variations therein, and then thermal state of the lunar interior by taking measurements well within terrain boundaries, and then use current impacts as a seismic source to aid in exploring the lunar interior. And you can see there in terms of magma ocean differentiation and potential overturn of that cumulate pile. And then René's paper, seminal paper in 2011, that put forward a model for the inner core, outer core, and then the partial melt layer at the base of the mantle. And again, this is base data, and this remains to be tested. We also have secondary science goals to characterize the present impact flux on the moon and attain fundamental information about moon plasma interactions. There's an exploration goal here to evaluate the seismic hazard to human outposts on the moon, and shallow moonquakes that can get above magnitude 5 based upon Apollo data. And there is a shallow moonquake origin somewhere around the south polar region of the moon. And again, Apollo could not constrain the epicenter of these moonquakes very well, because over here on the right, all of these occurrences were outside the actual network. And also document the meteoroid impact flux as well. There will be Earth-based support facilities such as laser ranging telescopes, and then telescopic monitoring of impact flashes during the week. We have these seismic sources to investigate the interior, as well as achieving our secondary science goal there of characterizing the present impact flux on the moon. So, baseline mission for identical landers globally deployed. You can see on the right our little inverted. This is a long-lived. We've got a 6-year mission with a goal of 10 years. So this will actually allow other nodes, maybe short-lived nodes, to be added by various means. So this could become the international lunar network of a decade ago, a network through having these long-lived anchor nodes, if you like. The 4 landers will be launched together and then deployed sequentially. Our threshold mission would be 2 identical landers deployed on the near side at number 1 here, the peak billion-year-old lava flows, well within the PKT, and then down in Shikard Basin, down here, which would be antipodal to one of the few far side deep moonquake nests, or approximately antipodal to that A33, which would allow us to the seismic waves through the deep interior moon, including the core here, and then record those same seismic waves from that nest through the P60 side here without going through the core. So we would just see the mantle, effects of the mantle and the crust at that site. I was going to say about that, that was very insightful, and I've just forgotten it. Brilliant. Anyway, sites, again, this would also expand the laser ranging network, and it would allow electromagnetic sounding well within the islands and the prosolarum creep terrains, and it will allow us to get a good idea of crustal thickness in these 2 distinct terrains. So the parent spacecraft would actually form the communications relay for our baseline mission, our far side landers, and each lander will be able to send data. We will make them identical, even the far side lander, so that if we have an anomaly, or we lose the orbiter before we've deployed, or we lose one of our threshold stations and we need to redirect the far side one, we can do that with no loss to the actual mission and being able to get data back. So that will be basically for the far side lander. We would have our landers on the near side be able to send data direct to Earth, although they could also use the ComSat if that direct to Earth capability is not available. So the instrument suite, we've got a lot of heritage. So we're adapting the very broadband seismometer from InSight, and that will be coupled with the 1 3-axis short period seismometer, again with InSight heritage. That we would also have a short period seismometer on the deck of each lander. We have an audio short period seismometer that would also contain 3 MEMS sensors. That would be buried via a honeybee pneumatic system from one of the legs, and again heritage through the DALI program with that. We have 2 heat flow probes, again deployed from 2 lander legs. The heat flow probe and the deployment system will be flown on the CLIPS 2022 mission. The 2 laser retroreflectors, there will be one on the deck and one on the lunar surface. These again will be flown on CLIPS 2022. And then there's one suite. We've got 4 electrodes deployed around the lander, fluxgate and search scale magnetometers on booms, and electrostatic analyzer on the deck to fulfill that suite. And then we've got 1 pan cam and 3 close-up images, and are more for looking at deployment and ensuring that deployment is optimal. And they tell you never put a table in a presentation, but there's going to be several of these. What we can see here is our mass, power, deployment power, data rates, cost, and notes. So I put this up just to demonstrate we've done a lot of work, and if you want to go through the numbers, which I did and found a few discrepancies, we're not just making it up. We've actually put a lot of work into this to understand the instrument suite. And this is everything that we would like to do, so we would reduce risk for the seismic portion of this particular mission, because we have a number of seismometers that will be gathering data. We have 2 heat flow probes in case we have a non-optimal deployment of one of those, so on and so forth. Science traceability matrix, and you can see here, I just put this up to show that for our primary goal and our primary objectives, we have traceability to the current decadal, the League Lunar Exploration Roadmap, the NASA Scientific Context for Exploration of the Moon report, and because I ran out of room, advancing SAT report from League, which was again looking at what progress had been made for the SCEM report. This also relates to our secondary science goals. Again, we've got traceability there. And then the exploration goal, we have traceability to the current decadal survey. So for CAD drawings here show how we would pack this together in a Falcon 9 heavy fairing. You can see at the bottom here we have the orbiter, which is basically the deployment spacecraft. We'd have 4 landers, 4 identical landers stacked up here that would also contain a 2-meter boom with 1 magnetometer to aid in our electromagnetic sounding. This is sort of supplementary science, because we really don't need an orbiter to do this, but it allows us to cross-check our electromagnetic sounding data because we have that orbital asset, similar to what 12 and the Explorer 35 satellite. Down here you see a lander that is got everything deployed with the different booms, the PanCam and the magnetometer booms. These little strings are the electrodes that are shot out as part of the magnetotelluric sounding suite, spring load, and these go in at 90 degrees from each other from each corner of the particular lander. Again, showing you the lander. These are new builds, and need to keep that in mind as we go through the costing. You see stowed different options for the landers when the instruments are stowed. On the left here, you can see this is our thermal control through louvers and heat pipes that would keep the interior of the spacecraft cool and warm. We have solar panels on 2 sides, so we need to ensure that our landing is optimal to be able to have good solar power throughout the lunar day. Again, looking up underneath, you can see here we have stored the VBB and the short period seismometer package underneath here, the lander. You'll notice there is no robotic arm as there is on InSight, because this is quite heavy, has a lot of moving parts, and we're trying to keep this simple. Again, looking at how we're packing everything together with the fuel tanks and the batteries, you can see here that so we have our landers put together quite nicely, at least in CAD and PowerPoint. So this is our goals and our objectives and our investigations led to a lot of mission requirements, and I put this in here to say that through this in a lot of detail, a lot of iteration, too many Zoom calls since the middle of March, that's for sure. But there again, it's good to talk to those folks from Goddard and our big science team, and sort of kept me sane over the last couple of months. So what we have here then, driving requirements, we have a Class B mission with a 6-year mission life with a 10-year goal. Our threshold mission, as I said, and our baseline mission we've already gone through. We need about 0.5 meter ground clearance. So we need to be looking for sites that are relatively rock-free. And this is useful because we have great imagery from LROC that we can now use to sort of mitigate the landing risk, at least in terms of the site conditions. The communication as asset is in orbit. It's that deployment spacecraft. Body-mounted instruments must be protected from the thruster plume, as we have to undergo quite an aggressive braking burn in order to deploy these. There will need to be some thermal protection around the VBB that's deployed under the lander. The sun angle will change over time, and while the thermal environment is quite benign under there during most of the day, when we get to early morning or early evening, then we start to get direct sunlight. So there will need to be some sort of curtain under that. Landing constraints. We will deploy with the 1/3 of the Earth. Fixed cameras can't be sun blinded, otherwise we're not going to be able to look at deployment. We've got to avoid rock-filled areas, so there may need to be some terrain relative navigation required. And although using local data in conjunction with the LROC imagery, I think we can mitigate that one quite nicely. The other thing for the landing constraint is making sure that the solar panels are properly oriented. And as you can guess, we're trying to do this without that option during this study. Night and day operations are allowed to be different, but data is taken 24/7, 365 or 366 if it's a leap year. So we need to make sure that we get all the data. So passive landing versus terrain relative navigation versus active hazard avoidance or combinations thereof. Power generation, solar array versus MMRTG versus combination thereof. Communications, direct to Earth versus orbital comm versus combination. And then we looked at data back. We looked at a number of different antenna. We could have a gimbaled antenna, but as that antenna tracks the satellite, then we're going to generate seismic noise, but hopefully that can be filtered out. And then we're looking at our common CDO and lander, and then thermal design trades, which for the moon can be a bit challenging. So putting the orbiters down, we've got direct transfer. We'll do a trans-lunar injection and then a lunar orbit insertion. And as you can see there, we've got a 50-kilometer polar orbit for deployment, and this requires quite an aggressive braking burn in order to do that. We did not look at the weak stability boundary coming in sequentially from L1, but that's done. So we do our phasing maneuver, we do our deorbit insertion to approximately 10 kilometers. Then our braking maneuver to bring the spacecraft to an altitude of 100 meters above the site, and then vertical descent to the lunar surface to land less than or equal. So again, this is how we looked at it, and the landing sites are shown there with our PKT, Shikard, Chrysium, and Korolev Basin sites. CONOPs for communication, near side land with a contact as backup, and then looking at KA or X-band for those particular communications. And the orbit for that COMSAT, you'll see in some of the charts, it's 250 kilometers. We just keep it the same. We're looking at, going to be looking at alternative orbits to increase because we did a study as part of this to show that if we need to rely on the orbiter to get all the data back, we can do that, including the near side sites. So power during the daytime for the avionics, and it's being scrubbed still, but nighttime goes way down. If we look at the thermal, we've looked at 0 degrees and 45 degrees. These are 2M members for our sites that we have to understand the thermal. And can come up with this the Louvers option for thermal control that has this is showing an earlier design with the deployable solar arrays. We went with something more simple, the fixed arrays, so we don't have any. We have fewer moving parts. If we look at this, we can control not only the temperature of the lander and the interior during the night and day, but what you see underneath there, where we're putting the seismometer and the heat flow probe and the buried seismometer. Thermal regime is quite benign at solar noon, and similarly at 3 p.m. But you can see as the sun is tracking, we're going to see some hot spots come in. Hence, we need to cover the VBB, which will be placed on the surface. So in terms of thermal, we've got high again battery heat pipes will keep things cool or toasty depending upon the time on the lunar surface. We need to vent the propulsion system, so we don't need to keep it. Don't need to waste power keeping that and again, we've looked at a solar, a purely solar mission, and it is closed, although it is quite large in terms of each lander with the number of batteries and the thermal design to keep those batteries alive. This is the nuts and bolts image, and again, lots of numbers to sort of get everybody confused. What I want to point out here, here's our launch mass. This is the number of landers, and I've gone too far. And what we see here, this is our launch margin. So what we have there are 4 landers with Falcon 9 Heavy. This is the cost over here with a 50% margin. The caveats down below are important because the cost input assumptions drive the results, and our lander is a new build. Orbital mass has not been audited and need to be updated. Again, this is based upon our concept study as of today. So the take-home message here is that there's more work to be done, but in terms of that work, we've actually examination the cost, CG Laddie. We've also looked at existing lander designs. For example, Insight is a great example, and also Phoenix, because Insight's based upon the Phoenix lander. And then we can explore other landing designs, such as Lockheed Martin Memsov can be developed into an LGN node and for that mission. So we know that a new build is possible, but we probably won't get the 4 landers if we go as is. But that to me is a requirement. More work needs to be done. Any questions?
Great, thank you, Clive. I think I'm going to take my prerogative as moderator and ask you a question. So this was there was a similar study done for the last decadal, and I'm curious about what changed and what didn't. What was the big developments in instrumentation or architecture?
In terms, well, let's go back to the last decadal. We looked at the International Lunar Network study was done before then, and then we had a concept study done as part of that last decadal, which we leveraged from. The biggest thing that has changed is the instrumentation in terms of the TRL with regards to seismometers, with regards to heat flow probes, the new next retroreflectors, the amount of development of the instrumentation has been quite phenomenal. In the Lunar was a mission that we did for discovery, proposed for discovery, which was the 2-node landing. And one of the major weaknesses was was too low of a TRL. So I think we've addressed that particular issue. So that's number one. Number two, as the battery technology has also evolved over time, so that if we look at the it's more massive than you would have just with an MMRTG. But you need to have a sophisticated thermal control for that MMRTG, because although Apollo lasted 8 years with their RTGs, this is not the Apollo RTG. It is a bit different, maybe for the moon, a bit less capable, although I can hear people at Glen Research Labs screaming now. But prove me wrong. But so there's the issue we have is that we went in and did a new design of a that is going to be a key mass and cost driver in terms of making this mission a reality. So that's why we're looking at existing landers and can they be modified to enable this particular mission. But you know, there's I think, and the area of future work that needs to be focused on as we move forward.
Great, thank you. Let's see. So we have a question from John Owens at Northern Illinois University. Do you have an estimation for the lowest magnitude quakes that could be detectable outside the noise? Wow.
All right. Well, number one, we got to characterize the noise of the lander. Number two, going into this mission, the mantra was it has to be better than Apollo. So we are looking at the VBB when it's modified to the moon to be an order of magnitude broader frequency range. And so I think that we will be able to detect very small moonquakes. The question is the noise, the lander noise, which needs to be characterized. So we have a training going now, an action going now to identify all potential seismic noise that would interfere with the detection. There's the neat thing about having humans there is they can move the instrumentation away from craft and cool down. But during the first couple of lunations, we're going to be able to characterize how the landers are going to behave. So once we get those and the frequency ranges that we have, then I think that we'll be able to subtract those out, trying to test the sensitivity on Earth. There's a lot of seismic noise, although the last 2 months that seismic noise has gone down a little bit. It's difficult, but the theory and the way the VBB is put out, and we will be better than Apollo. It's a matter of being able to quantify once we get to the moon how much better than Apollo will be.
I imagine we've learned a lot from InSight about these things. Yeah.
Yeah. Lots of things about it, but we don't have to worry about in terms of the moon.
Let's see. So we've got a couple other questions. We have a question from Suniti at LSU. What are the science team's plans for integrating regional bulk geochemical observations from prior missions with seismic insight into the moon's thermal history? We will be looking at the surface, which we've already done in terms of the terrains. What we'll be doing is exploring through a combination of seismic, electromagnetic sounding, and heat flow, what the composition of those are the questions we will answer, is to try and constrain what the deep interior of the moon is structurally, but also compositionally. So these data sets that we're getting back are very complementary. That's why I've chosen, so that we can actually model those, and we're not going to get it'll be based on a model, but the data that we will get will be of much better fidelity than we got
from Apollo or from orbit. So yes, we've already incorporated. It's just the surface. We want to know, well, what happens beneath those different terrains. So we're landing well within the terrain boundaries, and so we'll be able to address those questions by integrating these different data sets. And the other thing I will say is that fidelity and better fidelity to Grail data, because Grail data right now are based upon Apollo seismic data. So again, we will be incorporating gravity, the existing gravity data into interpretation of.
We have a question from Jim Cutts at JPL. Since there is no robotic arm, he would like some more explanation of how the seismometers are being deployed to the surface.
Okay, there is a crane, or basically a lift system. That's a package. The silicon audio MEMS is attached to one of the legs, and it's a pneumatic burial deployment using compressed gas, similar to the heat flow probes. So that's on the lander. So that's already there, and it will monitor how the lander behaves, and then we'll have one on the surface to be able to interpret the effect of the lander on our different data sets.